Daniel Manuel, and this is Lab 5. This lab will look deeper into Faraday's law, which relates time-varying magnetic field to a Curly electric field, whose path integral around a closed path is not zero, but it provides an EMF that can drive current. This current, in turn, produces a magnetic field, which exerts a force on the source of the magnetic field. In this lab, we will collect observational data of a falling magnet through a conductive tube of aluminum foil. We will model the magnet and tube interaction computationally, and we will compare our computational predictions with our observed data. Biot-Savart law, Newton's second and third laws, Ohm's law, magnetic force on a loop, the time derivative of magnetic flux of a dipole. The length is 0.3 meters, the width is 0.01 meters, inner radius is 0.02 meters, the radius is 0.03 meters. Mu is a value of 2.21 amps over meters squared, and that value was calculated from lab 3. The magnet's mass is 0.025 kilograms, and then the average time that it took for the magnet to fall through the tube is 1.63 seconds. Flow script code. In step 1, we initialized all the constants that we got from the geometry of the tube of aluminum foil. And in step 2, we created a function to calculate the magnetic field of the bar magnet, with the value of magnetic flux through each of the two rings in the tube. In step 4, we added a line to calculate the current within each individual ring. In step 5 and 6, we computed the typical magnetic field at each ring. In step 7, we calculated the gravitational force on the magnet, and then the net force with that gravitational force, and the magnetic force that was induced. And in part 8, we used Newton's second law to update the velocity and the position to be updated in the graph. The image on the left is the visual simulation of the experiment, and the right is the velocity time graph that was created from the following magnet simulation. The tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? From above, the blue current represents clockwise, and the red current represents counterclockwise. This is determined from Lenz's law. What happens to the dynamics of the system when you flip the magnet around? The only difference this would cause would be a flip in the direction of the current. How does the total time in tube of your real-world system compare to that of the computational system? How might the computational system be made more accurate? The total time in the tube was computed to be higher than it was in real life. To better predict with the simulation, you could add more rings in the calculation for the tube. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? At first, the force is unbalanced as gravity initially acts, and the magnet increases in velocity. But then as the forces are balanced, at the flat part, that is when the velocity is unchanged. Then at the very end, gravity is once again greater than the magnetic force acting in the upwards direction.